In this video, we are going to learn about two-component system. What are the different types of two-component systems? And one of the examples for this two-component system, that is lead-silver system with its phase diagram, and what is Patterson's process. Okay. Now, what is a two-component system? Okay. Two-component system is a binary system consisting of two different substances, and this two-component system is classified based on the miscibility of the two components in the molten state, or the nature of the solid phase that separates out during cooling, and whether the two components react with each other chemically or not. Accordingly, we can classify these two component systems into simple eutectic system, two component system with congruent melting point, and two component system with incongruent melting point. First, we will see what is a simple eutectic system. It's a binary system in which the two components are completely miscible in all proportions in the liquid state. Okay, and they do not react chemically. This is more important. This is just a mixture which is completely miscible in molten state, but there is no chemical reaction between the individual components. Okay, and each component has the property of lowering each other's freezing point, and such a binary system is referred as eutectic system. Okay, and the solid solution of such a two-component system, which has the lowest freezing point of all the possible mixtures, is known as eutectic mixture, and the minimum freezing point attainable corresponding to this eutectic mixture is known as eutectic point. Okay, and the example that we are going to study in this two-component system comes under the simple eutectic system, that is lead silver system, and another example is bismuth cadmium system, right? Okay, now we'll move into the second thing, two component system with congruent melting point. A compound is said to have a congruent melting point if it melts at a constant temperature into a liquid which is having the same composition as that of the solid compound. An example under this category, for this category, is zinc magnesium system. Okay, the next comes the two component system with incongruent melting point, and in this case the two components undergo chemical combination and forms a new compound which is quite unstable, and such a compound decomposes below its melting point to give a new solid phase and a melt with a composition different from that of the compound that's being formed. Okay, and the temperature at which the decomposition occurs is known as peritectic, meritectic, or transition temperature, and at this peritectic temperature the solid compound undergoes a phase reaction forming a new solid phase and a melt, and an example for this is sodium potassium system. So this is all regarding two component system and the types of two component system. Now we'll move into the example for two component system. As we have already stated, this two component, that is this lead silver system, is an example of simple eutectic system, which is otherwise known as easy to melt system, right? Okay, this is the phase diagram of lead silver system. We have taken temperature in the in the y-axis, and composition, which is expressed in percentage in this x-axis. So x-axis we have taken composition in terms of percentage, and y-axis is temperature. Okay, and this lead silver system is a two component system. Since there are two components, or it's a binary system consisting of two different substances, one is lead and the other is silver, and there are four possible phases. Can you tell what are the four possible phases? One is solid lead, the other is solid silver, the other is solution of lead and silver, and the other is vapor. Actually, there are four different phases possible for this lead silver system. But since pressure has nearly no effect on equilibrium, the system is conveniently expressed in terms of the TC curves. Okay, at constant atmospheric pressure, we have already stated in that reduced phase rule, when the effect of pressure is negligible, the pressure is kept constant and the TC curve is drawn. Okay, and as gaseous phase is practically absent in the solid liquid equilibrium of this lead silver system, and one variable pressure is neglected, we are going to apply condensed or reduced phase rule. Okay, what is condensed or reduced phase rule? F equal to C minus P plus 1. Here, since the number of components is 2, so F equal to 2 minus P plus 1, so F is equal to 3 minus P will be applicable, right? Okay. And when we see the phase diagram of lead silver system, we have two curves, right? AO and BO, and there is a point that is O, and there are different regions. We are going to study these things in this phase diagram, right? So first thing is the curve AO. First we will see the curve AO. The curve AO is known as the freezing point curve of silver, and it shows the effect of freezing point of silver on addition of lead in small quantities. We have already stated earlier. Okay, now we'll see this diagram. See, here it is 100% lead, which means pure lead is present in this side. This is 100% silver, which means pure silver is present in this side. On moving towards the left, okay, from this, when we are moving towards the left, the proportion of silver is getting decreased and the concentration of lead is getting increased. Similarly, when I mean concentration, it means proportion, okay. Similarly, when we move towards the right, the proportion of silver is getting increased and the concentration of lead is getting decreased, right? Okay. And this point A, it corresponds to the melting point of pure silver, and this point B corresponds to the melting point of pure lead. Okay, now we'll come. See, it shows the effect of freezing point of silver on addition of lead in small quantity. We have already stated in the previous videos that when some impurity is added to a pure substance, it lowers its freezing point. That is, this is a colligative property, depression in freezing point. Likewise, when some impurity, here what is the impurity? Lead. When this lead is added to pure silver, it lowers the freezing point of silver. That's why for 100% pure silver, it's 961 degrees Celsius. When small amount of impurity, say around 10% of lead is added at this composition, 90% silver and 90% silver and 10% lead. Note the freezing point. It will be coming to around this point. Automatically, naturally, it will be less than the freezing point of silver. Can you understand? So when some impurity is added to pure substance, it lowers the freezing point. That's what is stated in this curve, right? It shows the effect of freezing point of silver on addition of lead in small quantity, and it starts from the point A, that is 961 degrees Celsius, which is the freezing point of pure silver, where pure silver coexists as solid silver and liquid, since the vapor phase is neglected, right? And this curve indicates that the melting point of silver, it falls gradually on adding lead. Along the curve AO till the point O, that is 303 degrees Celsius is reached. What does it mean? At O, the solution gets saturated with respect to lead. At O, no more lead can go into solution, and hence the melting point of silver, it doesn't decrease any further. And if any more lead is added, it gets separated out as the solid phase, right? Now, can you tell what are the different phases existing in equilibrium along this curve AO? Okay, here we have already seen in cooling curves, no? When a mixture is heated above its melting point and brought to its molten state, and it's allowed to cool, when it attains the freezing point, one of the solid gets separated out as a solid phase. Okay, so when it reaches this point, what gets separated? This silver gets separated out as the solid phase, and the remaining portion, it's in the molten form. So the two phases existing in equilibrium along this curve AO are solid silver and melt. Melt means mixture of lead as well as silver in solution form, right? Okay, so can you predict the number of degrees of freedom for this curve? We know what is number of degrees of freedom for this curve AO. it's equal to F equal to C minus P plus 1. Since the number of component is 2, so 2 minus 1 plus 2, which is equal to 1. So the degree of freedom for this curve is 1. So to define any point along this curve AO, the minimum number of variables that has to be stated is just 1. If temperature is told, automatically the composition gets fixed. Similarly, if composition is mentioned, temperature is automatically fixed. Okay. Now, coming to this curve BO. So what is this curve BO representing? It represents the freezing point curve of lead. Okay. And it shows the effect of freezing point of lead on addition of silver in small quantities. And it starts from the point 327 degrees Celsius, which is the freezing point of lead, where pure lead, at this point, pure lead coexists as solid and liquid. And what does this curve indicate? It indicates the melting point. It indicates that the melting point of lead falls gradually on adding silver along BO till the point O is reached. And at O, the solution is getting saturated with respect to silver. Hereafter, we cannot add any further amount of silver to it. Or at O, no more silver can go into solution, and so the melting point of silver doesn't fall any further. And if any silver is added, it just gets separated out as solid phase. And along this curve BO, the phases existing in equilibria are, what are the phases existing in equilibria? It's a solid lead. As I have stated in this curve, the same thing. Okay. When it reaches the freezing point, when the mixture attains the freezing point, which will get separated, the solid lead gets separated, and the liquid or in the molten state, what will be present? Both lead and silver will be present. So it has two phases. One is solid lead and melt. Okay. So again, applying reduced phase rule F equal to C minus P plus 1, the system is univariant, right? Now consider this point O. It's the point where the two curves AO and BO meet. Okay. So what are the phases existing in equilibrium? Along this curve, solid, silver and melt. Along this curve BO, solid, lead and melt. So at this point O, what are the phases that will be existing in equilibrium? Solid silver, solid lead and melt. So what will be the degree of freedom? Which will, if we calculate, it will come to 0. So it's a invariant or non-variant point, and this point O, that is at 303 degrees Celsius. Okay, it represents a fixed composition of 2.6% silver. So remaining 97.4% lead. This corresponds to eutectic composition. So there are different mixtures possible, and each mixture will have its own freezing point. Of all the possible mixtures ranging from this to this, the mixture which is having the lowest freezing point is referred as the eutectic mixture. And so this eutectic mixture corresponds to a composition of 2.6% silver and 97.4% lead. Okay. No mixture of lead and silver will have a melting point lower than the eutectic temperature. And at this point, the temperature will remain constant till whole of the melt solidified en bloc to become solid of eutectic composition. On further cooling, it results in simultaneous crystallization of mixture of lead and silver in relative amounts corresponding to this eutectic point. And below the temperature line of the eutectic temperature, we have two regions. One is this region and the other is this region. This is eutectic and solid silver, where crystalline silver, this is eutectic and solid silver, where crystalline silver and eutectic are stable. Similarly, here it is solid lead and eutectic, which are stable. Okay. And the other is area above the curves AO and OB, are area enclosed by this region AOB, which is the liquid melt. So what is the number of degrees of freedom, which will be equal to 2. Okay. So in order to define any point in this area, we have to specify both temperature as well as composition. That's what it means. Okay. So this is all in the phase diagram of lead silver system. Curves, this point and these different regions. In the next video, we'll see about Patterson's process. Thank you.